All
All
right.
things are equal, but some are equaler.
Yes. One way to improve on Riemann sum approximations is to average the left hand and the right hand function values before multiplying by the width of the interval. Okay? This result gives you what's called the trapezoidal rule. And it's pretty easy to see.
Because it makes it trapezoid.
Yes, it would.
Whoa.
For those of you who can't immediately picture things in your head like that,
Like, you don't need,
Yeah,
you don't need to
that's
know
exactly what I was
like this. Look at it. It's a house.
That's a stop sign.
It says stops.
Or, I mean, that's what I meant.
so rather than using the left endpoint or the right endpoint for the height of this interval,
You made it.
you take the average
Oh.
and multiply by the width, which would be the area of this
Why
trapezoid.
would you not do that?
Yeah.
Why would you
You're
not?
Lazy.
It's a good question. I don't know.
Save time.
It is faster to do a Riemann sum,
Well, I want
Well,
But it takes longer to say.
but if you want a better approximation, a trapezoidal approximation is almost always better than a Riemann sum
Riemann
approximation.
sums are anti-communism. We don't claim them.
They're anti-communism?
You are
Why?
revolution.
Okay.
I think I Peter Fawn in on this.
So, a car accelerates to pass a car on a highway. The table below shows the velocity at selected times. Estimate the distance traveled by the car from 0 to 7 using a trapezoidal sum and the intervals in the table. Okay, so
Wait, what?
we're going
Look at those.
to use these intervals. And rather than use the left-hand velocity or the right-hand velocity, we just average those. So the distance is approximately equal to 1/2 of 81 plus 95 times 2 minus 0 plus half of 95 plus 103 times 3 minus 2 plus half of 103 plus 100 times 5 minus 3 plus half of 100 plus 81 times 7 minus 5. Feet.
Looks just great. You know, the 5 minus 3 really frustrates me, just because
and the 2
why?
minus 0.
It's 2.
Yeah, I fully understand that. And this is part of why we don't do a lot of the ones in the book, because they tend to do all of them equal width intervals. And on the AP exam, they almost never do equal width intervals.
It's not very nice.
Well, it just makes you,
Think.
No.
yeah, and that's sort of the point. They do want to see if you know it or not.
It's like you can get college credit from it or something.
Yeah.
You can live.
And if they're equal width intervals, there are simpler formulas that you can use, and your calculator that can be programmed to do that. I suppose that you could program a calculator to do this as well. Say, you know, this is what I put into the table. Give me a left sum, give me a right sum, give me a trapezoidal sum. In fact, as I know there is, and it's not hard, but they're going to expect to see your work. So if you just wrote down the answer, even if this was a calculator part, they'd be like, nope, no credit. All right, moving on.
That was easy.
So if a function is concave up, a trapezoidal rule is greater than the true value.
Makes sense.
If it was concave down,
Less.
it's the other way around, yes. Now, remember, and part of the way I remember the whole one about the midpoint is the opposite. So if you have something that is concave up like this, a midpoint, which would go to here, The midpoint sum underestimates because there's more that they don't get than they got extra here. I think it's easy to see whether a trapezoidal rule over approximates or under approximates. It's harder to see the midpoint one on some graphs. This one's not too bad, but sometimes it is. I just remember that they're opposites. Okay? All right, so another way to improve our Riemann sum approximation is to have more subintervals. Why is that? Well, this is approximately the same graph of f of x from a to b. If we only divide it into 2 blocks, we have all this missing area, right? Whereas we divide that into 4 rectangles, the sum of those little pieces that is left is smaller than these, right? So we're getting closer to the true value. It's a little bit like a pixelated picture, right? The problem with the pixelated picture is that it's clunky. They don't have enough pixels to make things look smooth. Like, for example, on your calculator screen, there are no curves, but there are enough pixels so that it makes it look curved. Okay, they're just lighting individual pixels and it makes it look like a curve, but it's actually a bunch of tiny little squares. Okay, it's the same idea. So, if we can find the limit is n goes to infinity, as I goes from 1 to n of f of x sub I times delta x sub I, our Riemann sum will no longer be an approximation, but the exact value, and that's called the definite integral. And we've talked about this already. Okay, just wanted to go back to that again. So the 2 ways to make your approximation better: trapezoidal rule, that's better. More subintervals, and a lot more subintervals especially, much better. Okay? So, for now at least, we're going to use our calculators to evaluate definite integrals. So, make this a little smaller so that we can see it. And yeah, in the end, I'm just going to leave it. It's fine. So oil is being pumped into a tank over a 12-hour period. The tank contains 120 gallons of oil when t is equal to 0. That's an important sentence. Students tend to blow right by that. It's going to be important to what we do. The rate at which water is flowing into the tank at various times is modeled by the differentiable function r of t. Values of r of t at selected values of time t are shown in the table below. So at time 0, water is flowing into a tank at 8.9 gallons per water, and it at least appears to be slowing down. We don't know that it doesn't speed up and slow down, etc. So estimate the number of gallons in the tank at t is equal to 12 using a trapezoidal approximation with the 4 subintervals from the table. It is really easy not to get all the points on this question, because notice it says estimate the number of gallons in the tank at time t is equal to 12 using a trapezoidal approximation. Students read that, all they read is trapezoidal approximation, they do a trapezoidal approximation and move on to the next part. But they haven't answered the question. The trapezoidal approximation is only part of it. The number of gallons is approximately equal to, it started with 120. It's really easy to miss that. And then water is flowing into this, so it's going to be plus the trapezoidal approximation. So that'll be half of 8.9 plus 6.8. And so that Ian's head doesn't explode, we'll just put 3 plus 1/2 of 6.8 plus 6.4 times 2. plus half of 6.4 plus 5.9 times 4 plus half of 5.9 plus 5.7 times 3. And there's no need to do anything else. You're certainly welcome to, but you're not getting any additional points for that. This counts both as showing the Riemann sum and getting the correct answer. This is probably 2 points on a free response question. It might be as many as 3. It won't be any more than that. All right, let's go on then. A model for the rate at which oil is being pumped into the tank is given by G of t is equal to 3 plus 10 over 1 plus the natural log of t plus 2. I want to know who came up with this model for this. And if I remember correctly, if you substitute in these points, you get pretty close to these values.
That's good.
So it's hitting close to those, or maybe even, within 1/100th of those. So use the model to find the number of gallons of oil in the tank at t is equal to 12 hours. Well, the number of gallons is going to be equal to, we started with 120. That's an important idea. Plus, this is the rate of change. What can we do to the rate of change to find the total change?
Some.
That would be to approximate it.
Integral.
Yes, we can do the integral. The integral of a rate of change, and to save time, I'm just going to write g of t dt. By the way, you can do that on the AP exam or on my tests or quizzes because it's already been identified. You don't need to write all that out. Okay? And I guess it should say, no, we're using the model. So the model says it's equal. So I'm just going to grab my calculator from there. Clear that away, 120 plus, and I encourage you to go ahead and do the 120 plus the integral instead of doing the integral and then having to remember to do the 120 at the end of the problem. So math 9. From 0 to 12 of 3 plus fraction with 10 in the numerator and 1 plus the natural log of x plus 2 in the denominator with respect to x. $197.975. Now I'm kind of curious as to what the other one estimated it at. Do you think it's going to be an underestimate or an overestimate? Well, let's see. This is a decreasing function. Let's assume that it's always decreasing. And it seems to be decreasing at a slower rate all the time, right?
It is an over-approximation.
So if it was decreasing at a slower rate, that would be concave up. So then a trapezoidal approximation will be an over-approximation. What does it come out to?
198.75.
So not bad.
Those are pretty large sums.
Yes. This is quite the large tank, apparently. Okay, any questions about any of that? All right, let me close this